First of all, thank you, ma'am, for the introduction. And I thanks to Dilip sir and his team for giving me this opportunity to interact with the young researcher along with some distinguished speakers. Now, I really congratulate organizing team to organize such a wonderful event because in India, even in abroad, now there are so many development is going in the field of the special function and fractional calculus. Nowadays, I cannot separate the special function and fractional calculus. Both are going together. So it is good event, and there are so many prominent speakers like Professor Mathai, Professor Menadi, KG ma'am, and Pathan sir, Devendra sir, and other speakers. So even from our PhD days, we have learned a lot from these peoples. So now it's a good opportunity for the some of the young researchers who begin their career in this field. It's a good platform for them to learn so many things that we learn in our PhD days. So basically, the theme of this webinar is the special function and their applications. Now, nowadays, there are so many theoretical papers published by several authors. There are very few papers on application side, even though we know that special function has so many applications in particularly mathematical physics and other engineering branches. Very few papers nowadays. A lot of generalized function have been developed. A lot of unification is going on, but still there are very few papers which have touched the application part of the such fractional such operators. So that's why I have took this topic to to spread the awareness of the application of the special function through fractional calculus. So that's why I have choose this topic, application of Mittag-Leffler function in image processing through fractional calculus. Basically, so my total overall the talk will be divided in three parts. So I will begin with the fractional calculus. I can see the list of speaker. Geji ma'am is there, Professor Menadi is there, Devendra sir is there. So I think these people are also touch fractional calculus. But I think this is the first talk regarding the fractional calculus. So I will start my talk with the fractional calculus, fundamental of fractional calculus. And then second, I will go in the image processing. And in the later part, we will see the fractional calculus and image processing. And in the later part of my this talk, we will also see the role of Mittag-Leffler function in image processing. And in the end, we will conclude with some recent development. So I think the young researcher will get some idea about the working in the application of the special function. So basically, to begin with the calculus, fractional calculus, let us start with the calculus. So basically, calculus is what? Calculus is a study of change. Whenever we want to model some change, so calculus will take part. And in calculus, we have two components, that is a derivative and integration. So derivative, we call it rate of change of. And integration, we call it area under the curve. For application part, it can be considered as area under the curve. It is a continuous summation. And we are finding a lot of application of calculus even in science and engineering. So there are some standard systems we have, such as RLC circuit, mass Springer system. And we have so many application of the multiple integral, classical integral. So we cannot even assume our study without the calculus. So calculus basically it is a study of change. So one natural question can be arise in our mind. We know that the derivative order is always an integer. Just we are taking that 1, 2, 3, and so on. So one can ask the question, why it is only the integer? So natural question can be arise in our mind. Why should not be a half order, to pi order, even in complex order? So we can think about the order of function, order of derivative as non-integer, 0.7, 1.45, and transcendental complex order. So the branch of the mathematics which deals with the derivative and integral of arbitrary order or complex order is called fractional calculus. So basically, fractional calculus is what? It is a derivative and integral of arbitrary order, real or variable. Now, some question can be arise in our mind, does it make any sense, or it is just any fantasy or any rigorous theories behind that? Some question can be arise in our mind. If it is make sense, then how to calculate the fractional derivative and how old it is? What are the percentage of the acceptance of the community, research community? Or does it have any meaning? Or why we should study it? Is there any application in science and engineering? So such question can arise in our mind before going to see the theory. So this fractional calculus is not a new branch. It is as old as the classical calculus. So once in a 1695, the dated 13th September, L'Hospital asked the Leibniz, what is the half-order derivative of function? Okay. So Leibniz, L'Hospital asked to Leibniz this question, and Leibniz beautifully replied this question, answer. This is a useful this is a paradox from which one day some consequence will be drawn. So with this answer, actually fractional calculus was born. So due to this date, so the community, the research community, celebrate the 13th September 1695 birthday of fractional calculus. So it is a very old branch of calculus, but there were no application at that time. So that's why this branch is developed very later. So basically, it is old as classical calculus. So there are some pioneer contributors in the field beginning from the 17th century. You can see that Leibniz, Euler, Lagrange, Laplace, Fourier, Abel. I think in 1823, the first application was developed by the Abel. And Liouville, Riemann. So now the question is, what are the rate of acceptance by the community? So till date, more than 15 books have been published. I think it will be more in number. Some dedicated international journals are there. Journal of Fractional Calculus, Applied Analysis, Progress in Fractional Differentiation and Applications. So some standard journals are for the fractional calculus. And first international conference was held in US in 1974. And one special international conference conducted every year, called every 2 years, called Fractional Differentiation and Applications. And recently in 2020, the first online conference on modern fractional calculus and application was held in Turkey. So now the research community is accept this topic, and now several people are working. Even so many people are working on that. More than 10,000 people are published on a single topic of the fractional differential equation. Now some fact about the fractional calculus. So already rigorous mathematical theory have been developed now. Now integer calculus is a special case. But geometrical interpretation, physical meaning also exists, but it will be not like the interpretation which we can give for the classical derivative. And there are more than 30 definitions of fractional derivative operators are there, even though it will be more than 30 nowadays. So actually, this is the beauty of fractional calculus. We have different definitions for the different situations. Under books on fractional calculus, so we can see that the book written by the Kilbas, Srivastav, Trujillo. In this book, even there are complex order fractional derivatives. Second one is Podlubani's book. This is a very important book because there are so many applications are also given in this book. We can also see the Miller and Rose book. There are some other books. And the Richard Herman's book, that is those who are from the physics background. So it covers so many applications in the physics. And lastly, recently one of the nice book which was written by the Shantanu Das. He is a former scientist in BARC. So he wrote a very wonderful, nice book, Kindergarten of Fractional Calculus. We cover from the even beginning to the higher level. So this is a wonderful. I strongly recommend this book. Those who are beginners. Now we begin with some basic fractional calculus operators. So we begin with the fractional integral, that is Riemann-Liouville fractional integral. So let nu be the non-integer fractional order, f be the piecewise continuous function on some interval. And the Riemann-Liouville fractional integral of f of order nu can be given by equation number 1.1. That is an integral 1 upon gamma nu, an integral e raised to nu minus 1 f of tau d tau. So this integral involves the power law kernel. Okay, so this is a standard gamma function. So this is called Riemann-Leibler fractional integral. If we see that nu equal to the integer, then it will reduce it to the classical integral. Now, second part is the Riemann-Leibler fractional derivative. The earlier it was Riemann-Leibler integral. Now second one is Riemann-Leibler fractional derivative. So we can see the Riemann-Leibler fractional derivative of order nu is given by the 1 upon gamma n minus 2 nth derivative of integral t minus tau n minus nu minus 1 f of t dt, provided the integral is exist. So this is fractional derivative, Riemann-Leibler fractional derivative. You can see that is an antiderivative of an integral. Now from seeing this definition, there are some observations which we can prove. Definition of fractional derivative involves an integration. Actually, we are calling it fractional derivative, but it is a classical integral. An integration is of the convolution type. And the kernel is weakly singular. You can see that. Here, the tau is running from 0 to t. So if we take t equal to tau, it will become non-singular. It will be singular. The kernel is weakly singular. It is of power law type. You can see that. So this is a power law kernel, and it is singular. These are the pseudo differential operators. So that is the fractional derivative, but it will be in terms of the integral. Now, another version, or if we see the advantages of this operator, because the derivative is the outside of the integral, so we don't require the differentiability of a function. Even we don't need the function should be continuous at the origin. These are the advantage of these operators. While this operator Riemann-Leibler derivative has certain disadvantage. So the biggest disadvantage of being used the Riemann-Leibler derivative is when we model the real phenomena in the real world problem. So we need to impose the initial condition in fractional form, and that will be very difficult to see the physically. So that's why this Riemann-Leibler derivative is not applicable in the real world applications, because the initial condition, if you model the problem with the Riemann-Leibler fractional differential equation, so initial condition will be fractional, and that will be very, even it is not possible to give the interpretation of that initial condition. Another disadvantage is Riemann-Leibler fractional derivative of constant is not zero. So that will be not somehow agree with some physical phenomena. So these are the disadvantage. Due to this operator is not useful in real world application. But later we will see that it has so many application in image processing. So I will show it experimentally how it will be used. So that's why Capito have developed another operator that is called Capito fractional derivative. Only the difference between the Riemann-Leibler and Capito is this nth derivative is inside. Instead, in Riemann-Leibler integral, it was Riemann-Leibler fractional derivative, it was outside that integral. So this derivative is just inside of this integral. So due to this is a very limited, this will cover very limited function, because in order to use the Capito fractional derivative, we need to have the higher differentiability of a function. Okay. So the differentiability of function is required, but this is very important. And if you see the most of the paper of the applications, you will find out this operator. The reason is when you model this, when you create a mathematical model using the Capito fractional derivative, so initial condition are classical initial condition. So it is very easy to give the interpretation of this condition. So for this reason, this is the most applicable definition of the fractional derivative. And one more thing, the Capito derivative of constant function is zero. So there are some advantage, and another advantage is the Laplace transform of Capito derivative. The Laplace transform of the Capito derivative, it is an extension of Laplace transform of the classical derivative. So it is very easy to deal with the analytic solution, even numerical solution also. So that's why this Capito derivative is applicable. But this operator also has some disadvantage. So if you see that here again the problem is that the range of tau is between 0 to t. So when tau is equal to t, so this operator is singular operator. Even though even if we use the Capito derivative in modeling, even the modeling has no any sign of the singularity, then also we have to use this Capito. So this is a issue that will be arises in the modeling of the non-singular system. So Capito derivative has two disadvantages. First one is, so in order to use the Capito fractional derivative, we should require the higher condition of differentiability. And one more is, not all system will follow the power law distribution. If you see the statistically, it will not follow the power law distribution. Even the singularity of this power law impose the model to be singular. So we have to use the singularity when we are model the problem with the Capito derivative. Even though system doesn't any sign with the singularity. So actually this will misleading the result. Okay. So in order to avoid this issue, even Capito himself gave the new operator, so that we will discuss later. Another definition is the Grunwald-Letnikov derivative. Most of the engineering people are using this. Even those people who are working in control theory, image processing, these people are using this definition. That is an extension of the classical definition of derivative. So this is called Grunwald-Letnikov derivative, and this is approximation. So most of the engineering people are using it when they are modeling. Most of the, I think, control theory experts are using this definition. So this is Grunwald-Letnikov. Later we will apply it in the image processing. We will see that the application in MATLAB. So earlier I told you that in Capito derivative, the problem of the singularity was occurred because the kernel was power law, that will be weakly singular. In order to avoid this problem, Capito himself gave the new definition of the fractional derivative, that call it Capito-Fabrizio fractional derivative in 2015. So they use exponential kernel. So they use exponential kernel instead of the power law. So using this operator, they are giving some beautiful result. So nowadays there are so many papers published on mathematical modeling with the Capito-Fabrizio fractional derivative. So this advantage is this kernel is non-singular. Even the system has no singularity. So this is a very important definition. That is an important application of that operator. And in the same year, Professor Balianu and Professor Atangana, they have developed another definition that is called Atangana-Balianu fractional derivative. So instead of exponential, they have used Mittag-Leffler kernel. This is a very important function, special function, which is closely related with the fractional calculus, because most of the fractional differential equation have solution in this. So they have used this kernel. Now what are the advantage of this kernel? This function is non-local function. Look at that. We have the parameter nu. So this is a non-local kernel, and exponential is a special case of the Mittag-Leffler. So this is a non-singular as well as non-local kernel. So this operator work significantly. So where the Mittag-Leffler function, that is an extension of the exponential function. So you can see that this is the definition of Mittag-Leffler function. Now these are the why earlier I told you that special function and fractional calculus closely related to each other. The reason is that because there are so many functions which appear as a solution of fractional differential equation. One of them is Mittag-Leffler function, right function, Menardi function. So these are the functions which arises as solution of fractional differential equations. So even we have seen that some of the paper against this operator. So not total community have accept this concept. But what I have, this is my own point of view. In some situation, this operator working very well, such as the image processing. I will show it today experimentally. So this operator work, this Mittag-Leffler function play a very important role in image processing. While in the case of the viscoelastic modeling, this operator is not working very well. So there are not any significant results are obtained. Okay. So actually, this is the beauty of fractional calculus. We have the different type of definition for the different situations. Okay. Now, so these are the generalized Mittag-Leffler function. So the two-parameter Mittag-Leffler function is defined by this series expansion. This was given by the Wiman in 1905. And then one more generalized Mittag-Leffler function, which is a three-parameter. So it was introduced by the Prabhakar in 1971. These are the generalized Mittag-Leffler function. So after that, there are so many generalized version of Mittag-Leffler functions are available. When the people have generalized, they introduce more variable, they have introduced more parameters, even they have developed the matrix analog of this. So there are so many kind of generalization and unification of Mittag-Leffler functions are available in literature. These are the integral. So whenever we have a derivative, so we require antiderivative. So this is a Tangana-Balenu integral. So this is the integral that is antiderivative of the Tangana-Balenu fractional derivative. We can see that. So to know more about these operators, you can see that these two papers. So one of the very interesting paper was written by the Professor Atangana and Professor Gomez, that is decolonization of fractional calculus rules. In this paper, they have beautifully expressed the importance of Mittag-Leffler function statistically. So why this kernel, the Mittag-Leffler kernel have significant result, gives the significant result in modeling. So I must recommend the young researchers to read this paper. So you will find out very interesting properties of Mittag-Leffler function in this paper. Why they have choose the Mittag-Leffler kernel? They have correctly argued that. So now, so these are the fractional derivative. Now, if you see the fractional differential equation, the fractional differential equation, that is differential equation involving fractional derivative. As for example, look at that. This is a fractional Mittag-Leffler equation. It is a half-order derivative. So this is fractional, and this is useful in oscillatory process with damping. Okay. So this theory is also properly developed. Ordinary differential equation as well as partial differential equation. Linear, non-linear, existence, uniqueness, solution established. See, sometimes analytic solutions are very difficult to evaluate. So people have also developed the numerical method to solve the fractional differential equation. Now in the end, this is a summary of this development. Now if we see that fractional derivative, which all are involve integration. And while you deal with the classical derivative, that is the derivative, that is a limit at a point. So integration is a non-local operator because integration is defined on an interval. So fractional derivative is non-local operator. Now, this is a very important thing. When you calculate the time derivative of a function at some point, the system has to remember all past points because its derivative, its definition is the integration. The fractional derivative can be used to modeling system with the memory. When the system has to remember the past memory, so in that case, fractional derivative is a good, is an excellent tool to model the system. So that's why the fractional modeling right now becomes so popular due to this reason, because it is non-local and there are some systems with the memory, it can be modeled beautifully, accurately with these operators. So now, what are the applications? So earlier we have asked the question, what are the applications? So actually this branch was developed in 1695, but applications are just only last 14 years old. So there are two kinds of applications, modeling the system and the control, fractional order control. So in almost all branches now people have found the application of the fractional calculus, viscoelastic materials, polymer materials, so all these things. In signal processing, chaotic image processing, astrophysics, in almost all branches they have found. So this was the first part of my talk. I will move to the second part, that is image processing. So basically my talk is on the application of the Mittag-Leffler function in image processing, but I will explain it through the fractional calculus. I will begin with the fractional calculus. I will move to the image processing. Basically, the question is what is image? So image is mathematical, it is nothing but the two-dimensional signal. It is a function of two variables. Okay. So in terms of the MATLAB, it will be nothing but a matrix. Whose can be whose function is, which is ultimately the function of two variables. Okay. So I will show you in the MATLAB what is the image and how can we deal with the image processing using this our special function and fractional calculus. So digital image processing. So basically image processing is, it is a process of digital images some computer softwares. So basically image processing is nothing but processing of the images using computer softwares. So there are three kinds of image processing: low level, mid level, high level. Low level, that is noise removal, image sharpening. Mid level, that is recognition, segmentation. High level, that is scene understanding, autonomous navigation. Still, I'm telling you that not still fractional calculus have not still proper application. People have developed the proper algorithms for the image processing. So many open problems are there in this field. It is a wonderful topic for the young researcher. Now, why image processing is required? Basically, when sometimes we receive the images from space or either from some underwater images, so it will be not clear. So we are not getting proper information. So using some mathematical algorithms, we can give the proper interpretation of that image. So that's why some processing is required. So actually processing of image for storage and transmission. So sometimes this plays a significant role to get the information from the images. So those who wants to see some fundamental of image processing can read this book. It is available in Google. It is Gonzalez and Woods. It is a very nice book. So there are three kinds of image. We have RGB. So look at that. All the examples are given. Second one is grayscale. Third one is a binary. All these are the accepted formats. Now, representation of image. See, these things are very important to understand before I'm going to take the special function part. So what is image? Image is basically nothing but the rectangular array of integers. Basically, it is a matrix whose entries are the pixel values. So image of size m cross n is given by the rectangular array, and whose entries are nothing but the pixel values, which can be given by the functions of two variables. Okay, so in MATLAB, we can give the n by n array in this way. So this is the array. So basically, this is my image. Later, I will show you in the MATLAB. Now, one more concept that is important to understand is mask. So mask is already image is nothing but the rectangle or a matrix, and mask is the small rectangle that we are going to implement on the original image. So the image can be, so we are getting some processing of the image. So ultimately we have to create one more rectangle or one more matrix that is going to implement on the original image. Okay, so that is called mask. Mask, that is a rectangle or other shape over the given image. A new image whose pixels have gray value calculated from the under the mask. So exactly we already have the image. We are going to implement the one more rectangle that is called mask, and there will be some procedure. Even some operation will occur between the image and the mask, and we are getting the new image. Okay, we are getting the new array. So that will be actually process the image. So I will show it these things in experiments. So suppose this is my part of my image, and this is my mask. Mask also can be called filter. So if I implement this filter on my image, so look at that. So each element will multiply by the corresponding element of the filter, and they will be added. So the new value will be replaced in the middle of this image value. So this will happen to the each element in the image. This each element to the image. So image have some new value. So that will give the new effect in the image. So ultimately now our question is how to generate this filter. Only our investigation is how to create this filter. Okay. One more thing is that is edge detection. This is also one of the branches of the image processing to detect the edges, because this is very useful in the physics. Even the image is coming from the space, so they are interested in some edges to detect some edges. So that is another branch of the image processing, that is edge detection. So they are using these four operators, these two type of matrices they are used, Prewitt and Sobel operator. Now instead of these two, so first we will later in my last part of my talk, I will implement these two matrix on image, and I will also implement the fractional mask on the image, and we will compare the result. Usually these are the standard operators which people are using to detect the edges. So I will show all these things in MATLAB. If you are interested in the fractional order image processing, so first you should read this paper. This is a review paper which is available. It is a very nice paper. So this is a general algorithm. How can you deal with the image processing using the fractional? So first of all, you should have an image. You have the integer order method, and then you will generalize. Either you can take the Riemann-Levelin operator, Krunal Letnigo, Capit, or you can take this Tangana-Baleno operator. There are some more operators are there. Use the discretization method, obtain numeric solution, and make a mask. So this is algorithm. So these all detail are given in this review paper. So those who are interested in this topic, you should read this paper. Now, image enhancement. Now, what is image enhancement? So basically, image enhancement is a procedure to improving the quality of image to get the some useful information from the image. So basically, it is a process to improving the quality. Okay. So there are some methods to enhance the image: frequency domain method, spatial domain methods. Okay. Now, the one can ask the question that what is the theoretically proof that the fractional image processing will give the better result than the classical differential operator. So I will represent these things using the Fourier transform. So integer order differential operator performs better for high frequency feature of image. I told you that is Sobel private operator. So this will be working fine when we have high frequency feature. But whenever we have the low frequency images, so the integer order are not sufficient to perform better. But in that case, we had a fractional, we had a tools, fractional tools to deal with the image processing. Okay, and fractional order differential operator has capability of not only preserving the high frequency contour, but also improving the low frequency texture detail. The classical integer model will working well in the high frequency images. Whenever we have low frequency images, the fractional will be working very smoothly in both. Okay, high frequency as well as low frequency. I will show you the reason also why it will be working very well. So look at that. To understand this, let us see that. Assume that this is an image we have. Okay. So we have the image. It is a function of two variables. So let us implement the fractional derivative operator on the image. Okay, so this is the fractional derivative. This is a fractional derivative of the image. So we had applied. Now let us apply Fourier transform. If we apply the Fourier transform, this is the Fourier transform we have of fractional derivative. So you can find out all these formula that in Podlubani's book. So this is the Fourier transform. So we are getting this. So now we have actually two domain, time domain and frequency domain. Okay. So we can draw the graph for various fractional derivatives. Look at that. So on x-axis, I have taken a frequency. On y-axis, I have taken amplitude. So for various fractional derivative, we had drawn the graph. Look at that. So as we change the order of fractional derivative, we are getting different graphs. Okay. So frequency versus amplitude. Now, so these are the frequency amplitude graph we are obtaining when we have implemented fractional derivative or integral on image. Now, what are the analysis from the graph? So you can see that is the increase the order of fractional derivative, the Fourier amplitude decrease and frequency increase. Okay, see classical derivative, in classical derivative we don't have any choice of order. We cannot control the process. While in the fractional we have controlling parameter in our hand. Our fractional order are the controlling parameter in our hand. So you can control your system. If you increase the fractional order derivative, the Fourier amplitude decrease and frequency increase. Now the larger the frequency, as the frequency will be increased, the shorter distance between the function and the edge of the image. This is very interesting. As the frequency, and this thing is not happen in the classical derivative. As the frequency increase, the distance between the function and the edge of the image become less. So we can cover more edges of the image. And the larger the gradient of the image. So the gradient of the image will be larger. So therefore, the gradient of the image can be characterized by the frequency. The larger the frequency, larger the gradient. So frequency areas are more closer to the edge of the image. Okay. So when the fractional order, and differential order get close to zero, the area of the corresponding image tend to be smooth. So that is an advantage of fractional derivative. So we can cover more area of image. Okay. Now, how to create this mask? Earlier I told you that we had original image and we have the mask. The only question is how to create the mask. So now I will discuss how to create the mask for the image processing, and later we will see how can we use the Mittag-Leffler function. Now, so in 8 direction we have to create the mask. So these are the 8 direction we had the mask. These are the 8 direction along which we have to create the mask, and we have to put it so it will be create a general mask. Basically, mask is nothing but the matrix. So look at that. This is a general mask. When I put it the mask in each direction, so this is the procedure how to create this mask. There is a paper, so I will cited all this paper in this, and I will also share this presentation so you can see that you can read all this procedure, because in this time I cannot cover everything. So this is a general mask that we have created. Now only thing we need to find out, so these all are the coefficients that we have to find out by applying the discretization of the fractional derivative. So this we need to find out this A0, A1, A2 and these coefficients. Now look at that. This is a general mask. Now centrally we can take it 3 by 3 or 5 by 5, 7 by 7. So it is ideally to take the odd order mask 3 by 3, 5 by 5, 7 by 7, 9 by 7. So if we take 3 by 3 the center, so I will get it these 3 masks. So 3 by 3 fractional mask. If I will take it the 5 by 5, I can take it this 5 by 5. Look at that. So here I have mentioned. So you can use either 3 by 3, 5 by 5, 7 by 7, whatever you use. Whatever the good result we are getting. So in some paper I have seen they have used 5 by 5. In some paper they have used 3 by 3. So today I am going to explain how it will be work on image. Whether you are taking 3 by 3 or 5 by 5. Now I will take some operators. I will start with the Krunal derivative. Earlier I had defined this. Operator. So this how we can see the Krunal-Letnikov will play the significant role in image processing. Okay. So this I already defined earlier. Now, so this is the discretization of the Krunal-Letnikov definition. It is available in this paper. You can see that. So if we apply the Krunal-Letnikov derivative on a function, so it can be discretized in this way. In 2-dimensional, it can be written in this way because our image is a 2-dimensional function. So basically, when you apply the fractional Krunal-Letnikov derivative on the image, so you are getting this discretization. So this is in y direction. So look at that. What are the coefficients? The coefficient of f is 1. Coefficient of the second part is minus mu. This is third. So this is my A0 is 1, A1 is minus mu, A2 is minus mu plus 1 by 2. So look at that. These are my coefficients. So basically, these are the coefficient of that matrix, that filter. Earlier I show you that. So these are my coefficient. So basically, what I have to do, I have to implement the fractional order derivative on image. I need to find out these coefficients, and from that I have to create that matrix. So simply, I am getting my coefficient A0, A1, A2. So these are the coefficient which I have obtained by using the Krunal-Letnikov derivative. Okay. So look at that. This is my matrix. This is my mask, 3 by 3 mask. This is my 5 by 5 mask. Okay. So this is the in this way I can obtain my mask. Okay. So this is 3 by 3 and also 5 by 5. Now I will show you in MATLAB how it can be implemented on image. Okay. So now let me go to the just a minute. Can you see my MATLAB image? Can you see my MATLAB screen?
No.
Just a minute. Okay.
You just share the entire screen, then it will.
Okay. Now is it visible, sir?
Yeah, now it is visible. Yeah.
Okay.
Yes,
okay.
yes.
So I will show you how it can be implemented on the image. So I already have prepared this command. First, I will lead one image. Look at that. This is one of the image, that is astronomical image. So there is a one criteria to check the information on image, that is called entropy. Later I will tell you what is the meaning of that entropy. So entropy of this image is 7.12. So as the more entropy, the image has more information. That is a probabilistic definition. So that is one of the criteria to check the quality of the image. So as you increase the entropy, the image has more information. Okay. Now I will implement this mask. I will choose the fractional order 0.5. Not necessary that, but I had verified that it will give me the better result. So this is the mask which I have obtained by using the Krunal definition. Now I will see the result. So I will implement on the image. So there is a procedure in MATLAB. I will show you both the image together. You can see on my screen. The left hand side image is the image, the usual image. The right side image is the image which is processed after applying the Krunal mask. Now let us see the entropy of the second image, the new image. So if I find the entropy of second image, look at that, it will increase. So we can enhance the image by using the Krunal. Still, I have not used any special function here. These are the Krunal definition of the image. So, okay. So can you see my presentation now?
Yes.
Okay. So this is the mask that we had implemented. It will work better. Now these are the entropy that we had used. Entropy, that is a probabilistic definition. That is a randomness of the image. If the image has more entropy, that information image has more detail. Okay. Now another is the fractional, the Riemann-Leibler integral or Riemann-Leibler derivative, you can say. So the mask we can create by using the Riemann-Leibler integral. Look at that. These are the discretization of Riemann-Leibler integral on image. This is my image. If I apply the Riemann-Leibler integral, I am getting this discretization of that. So this is also available in this paper. So from that, we had create the mask. Look at that, A0, A1, A2, A3. And these are the masks which we have obtained by implementing this discretization with Riemann-Leibler fractional integral or derivative. You can say this is the 5/5, this is 3/5. Now I will show you the performance of this. I already have this. So let me clarify all this. I will show you the performance of this. So I will lead the image. This is the image that I have read. Now this is a simple image. Now I will add the noise, because what happened? Sometimes the images comes from the space and that is full of the noise. So we will see the denoising part. Okay, how it will be denoise. So I will add the Gaussian noise. So I will show you. Look at that. There are two images on your screen. The left hand side is the usual image, and the second image is the image obtaining after adding the noise. Now suppose this noisy image is with you. Now if we implement the fractional mask, that is the Riemann-Leibler definition, I have choose the order 0.7. So I have used this mask. Look at that. Oh, this is actually the new image after implementing the mask. So after implementing the Riemann-Leibler mask, I will show you this, both the image. Now look at that. The first image is the noisy image. Second image is the image which is after implementing the Riemann-Leibler mask. So little bit noise is, you can see noise is removed, little bit, not much. Okay. So if I find out the PSNR is another criteria to check the image. Look at that. So the PSNR of the noisy image is 19.9, and after implementing the Krunal Riemann-Leveller fractional derivative, we are getting 21.78. So these are the advantages of the fractional calculus in image processing. Now I come to my topic. Okay, so this is the PSNR, that is another criteria to check the performance of image. So these are the formulas of PSNR. Okay. So as the higher the PSNR, the better quality of the compressed or reconstructed image. Exactly, PSNR will play the role when we have the reconstructed image. Okay. Now I come to my main topic. So that is Mittag-Leffler kernel. See, earlier I had defined the fractional derivative with the Mittag-Leffler kernel. So in my previous two experiments, there were no any role of the Mittag-Leffler function. But now this is the mask which Professor Atangana and Ganbari have obtained using the Mittag-Leffler kernel. Okay. So now I will check the performance of the this with the Mittag-Leffler kernel. Okay. So again I will show you this performance. I will go with the same image. Okay, I will go with the same image. So I'm adding also the Gaussian noise. So I will go with the same image. Okay. So I have taken the same image and I have added the same noise. To see that, so we can compare the result of Riemann-Leveller and at that Mittag-Leffler kernel. Now I choose fractional order 0.7. So I think I have randomly did it, but we can find out the best, or even we can find out in paper. So this is the mask that obtained by using the Mittag-Leffler kernel. So look at that. This is the mask, or this is here I'm using 5x5 matrix. Earlier I had used 3x3. So using this 5x5 matrix, this matrix was obtained by the Mittag-Leffler kernel. So I had implement on the image. If I implement on the image, look at that. So look at that. The left hand side is the noisy image. The right hand side image is the image obtained by the applying the mask with the Mittag-Leffler kernel derivative. So this is the actually importance of Mittag-Leffler function. And due to the non-local nature of the Mittag-Leffler function, it can cover more part of the image. Now let us see the PSNR of both these. So if I find the PSNR, look at that. The original it was 19.07. By using the Riemann-Leveller, we found 21 point something, and with the Mittag-Leffler kernel, we had 23.06. So we are getting better result while we using the Mittag-Leffler kernel due to the non-local nature of Mittag-Leffler kernel. Okay, so it is a very good work for the special function people to obtain the better result with the generalized special function. Okay. Now, in the last part of this talk, that is the last experiment I will show you in 8 detection. Earlier I told you that in 8 detection either Perwitt or Sobel operators are used. But here in this paper, Ganbari and Atangana, they have developed the fractional mask using using that Mittag-Leffler kernel for 8 detection. So earlier I show you the image denoising. Now I will discuss. So again, look at that. I will take the same image. Okay, so I am taking this image now, the second one. Now I will use the classical matrix that generally people are using it. That is Perwitt operator. So this is Perwitt, horizontal Perwitt operator. So I will use the Perwitt operator and I will see the result. I will show the result. Look at that. This is the second image, that is 8 detection. The idea of 8 detection is to detect the edges. So using the Perwitt operator, we are getting this figure. We are getting this image for 8 detection. Okay. Now I will use the fractional mask with the Mittag-Leffler function. So I will choose 1.7 fractional order. and I will directly show the performance of the fractional mask. So these are the matrix, these are the operator, these are the matrix which we have obtained from the Mittag-Leffler kernel derivative. Now I will show the performance of both these, gate detection. So I will show you, look at that. The first image is the 8 detection by using the classical derivative or the classical operator. Second one is the 8 detection by using Mittag-Leffler kernel derivative. Okay. So the second image is the more information, more edges to be detected than first one. Let us show the PSNR, let us find out. Look at that. The first image has the PSNR of 5.9 and in second it will be improved. So due to this Mittag-Leffler function, we are getting the better result in 8 detection also. Earlier we got that the best result in image denoising. This is 8 detection. So there are 10 to 12 branches of the image processing are there. So I am only touch only 2. So what are the possible areas of the application of even fractional calculus and special function in image processing? So image enhancement, image denoising that I already show you, 8 detection, then segmentation, registration. These all are the field which are possibly still not proper work have been done. So many things still are open. Some of the recent development you can see some of the papers they have used the Krunal, Letnikov, Riemann-Liouville derivative, 8 detection. And we can see these papers. Even though I can see on the 24th we have a lecture of Devendra sir, they are going to cover fractional operator with special function. So one can find the application of this operator in image processing. Even also Prabhakar integral. See, I have not seen a single paper on image processing and Prabhakar integrals or Prabhakar derivative. So one can think over it. Yes, so with this, sir, it is open for any question with permission of chair.
Thank you so much for such a wonderful talk. You